Hello everyone and welcome back to this next lecture in the machine simulation lecture series. And this is where we had left off in the previous lecture, where we had started with changing our variable load to a current source representation. So to be precise, if we go over to our circuit file and we see that in this main simulation where we had a resistive inductive load which was being supplied by a single phase voltage source, we have now replaced that by a current source. And this current source was being conceived by a controlled voltage source in series with a variable resistance. So this representation of any variable load can be extended later to any kind of system, even an electrical machine. And this is what we'll look at very soon in the coming lectures. So as always, before I start this lecture, a little bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses on the MOOC website Udemy. So for that, all you have to do is go to my own website, which is pythonpowerelectronics.com, and in that, just go and click on this button, Learn. So these are the courses which I have currently. Most of them are being hosted on the MOOC website Udemy. So if I just go ahead and have a look, the very first course is simulating power electronic circuits using Python, and in this I talk about the very basics of how you can use Python and Python power electronics to simulate power electronic circuits. The next course is on signal processing, and in this I talk about how you can use Python and Python packages like SciPy and Signal to design and analyze filters that we can also simulate using Python. The next course is more on simulation of magnetics for power electronics using Python, and in this I talk you how you can simulate magnetic components like inductors, coupled inductors and transformers using Python and Python power electronics. After that, I have the course on control analysis with Python for grid connected converters, and in this I talk about how you can use Python packages like Python control to design and analyze controllers for power electronic applications. The very latest course I have is Why Specialize in Power Electronics, and this course is more targeted towards maybe junior undergraduates or maybe even high school students, and this is a free course to motivate people to choose power electronics as their specializations, and it talks about the challenges and opportunities available as a power electronics engineer. So the link for this page is provided in the description for this video. If you're interested, please do check it out. So coming back to our simulation. So we had already edited the resistive RL load, and in this I had uploaded the parameters from the previous simulation. So what we need to do is to edit the parameters of the current source load. So let me click on this button, and here you'll see these are all at their default values. So now let's start going and changing them. So the very first one, which is the ammeter. So let's go to our circuit and have a look. This is the ammeter. Now, since this representation is for a load, you would expect that this would draw a current. Okay, this is important to note that in such a representation, these can very easily change. For example, if you have an electrical machine that can behave both as a motor and a generator, there is no hard and fast rule as to what the current should be, right? So for example, if I say that a direction of current is such that it is flowing downwards because it is a load, if I were to reverse the current, it becomes a generator, in which case it is supplying power. So this is just simply for reference. But I could choose this ammeter such that it is drawing a current. So I will say that this polarity should be downwards with respect to the component. So let me go and do that. And here you see the component position is at 12F. The positive direction is 11F, which is actually the reverse. This should be below the component. So let me change that. So I'm going to make this one position below. So therefore, the positive polarity is downwards. So I'm going to save this and keep going. After that comes the control voltage source. So now the control voltage source needs some changes. So I'm going to change it. Now let's go back and have a look at the circuit again. Now this control voltage source can be, again, is just a reference. We can conceive it in different ways. But as I said, the idea is to adjust this control voltage source with respect to the voltage across these terminals such that we draw a certain current. That is the objective. So if we consider this voltmeter to be measuring a voltage such that the upper terminal is positive with respect to the lower terminal. In that case, it makes sense that we also choose the polarity of this control voltage source such that the positive polarity is upwards, so that they are just compatible, right? Now, let's go and make that change. You see that the component position is at 4F, positive polarity is 3F. So it's already pointing upwards. I don't have to make any change. I would, however, change the control tag. Though it is not really necessary, I would still maintain unique values. So what I will do is I'll change this to the name of the component. Right? The initial voltage can be 0, no problem. So I'll save it. And we are done with this. Now let's go over to the variable resistor. Now the variable resistor does not have a polarity. So that way we are kind of thankful. However, you do need an initial voltage, initial resistance. Now we are going to set the value of the resistance in code, which means we are going to program this. So all we need is an initial value, and the initial value of 100 here is perfectly okay. So I would leave it as it is. The only thing that needs to change is the control tag, which I will make the same as the component name. So let me just go and paste this here. And let me come down. The last one is the voltmeter. So now the voltmeter again, as I said, we are assuming that the positive terminal of this entire combination is upwards, right? So the voltage is like kind of upwards positive, downwards negative, right? Again, just a convention, but that means this polarity of the voltmeter has a positive polarity in the upward direction. So which means, let me go edit it. You see that the component position is at 8C, positive polarity 7C, which means it's already upwards. I don't have to change it. What I would change is this rated voltage, right? Now, depending on the rating of our system, I would choose it to be much larger. Now we are choosing a 240 volt system, which means the peak is around 340 volts. So let me make this 1000 to be much larger than the rated voltage. So this way we can guarantee that it always draws a negligible current. So I'm going to save the parameters, and with this we are done. So since we are done, let's quickly export the parameters so that we can always use it again. So with this we are done with this. Let's go back to our main page, and now we have to edit a control. We need a control. Now we already have this load variation. So instead of going and creating a totally different file, I can just change this itself, right? So let's go configure control. Now I have these two values. These are no longer applicable for the simple reason that we don't have them anymore. So let me go and delete them and get rid of it, right? So this means that now we have, let me go and now create another file. Actually, we don't need to create another file. We already have this file. Let's use it. So I'm going to wipe this out because this is all no longer necessary. We had this already here, so we are not losing any data. It's just we already copied everything over. So to get started, what do I do? Now, there are various ways in which we can do this, but now I would like to actually write control code. Right? Now, there are various ways in which we can do this. As I said before, we'll start with simple and then progress to a more complicated value. So let's take, for example, let's just take the simplest case of a control output only. So let's just adjust our control output and see what we get, because this is the simplest way to get started. So what that means is, let's add a control file, a control output. Now we have two controllable elements in our circuit. That is the control voltage source and the variable resistance, right? These replace the variable resistance and the variable inductance. So let me go over and connect them. So the first one is this. Actually, this is probably a bug. These two should not be there because I have removed them. So this is probably a bug. I'll have to look into it. So now that this is there, this is the control voltage source. So I'm going to give it a name that I'm going to use in our control code. So let me call this voltage output. The initial value can be 0. Save the value. And the next one is the variable resistor, right? Again, there's a bit of a bug. There are two variable resistors. This one should not exist. I will have to look into it why it exists, but we will have variable resistor instead. This is the one which we have currently used in our circuit. Just in case you want to confirm, go and have a look. This is the name of it. Right? So I may choose it again. This is what it is. And I will call this series resistance. Right? Probably not the best name, but that's okay. And let me give it a value of 100. Save the output. Right? So if I take just these values, all right, so this value is initially 0. This is actually good enough to run. For example, if I go back to the main page, right, and let me go and do nothing here, right, there's absolutely nothing. So I have a blank load file, a control file. It doesn't matter, because what is happening is, just in case you're confused, we are setting a control output to be 0 volts and a resistance of 100 ohms, right? So what this means is, if we have a look here, there is no voltage, but you have 100 ohms, right? So should this work? There is one little bug and we're going to solve that, but that's different. But technically this is all we need, right? Because we can set this voltage to 0 and we can put this resistance to a certain dummy value. This should be good enough to run. So let's go over and have a look. Like I said, there is one little bug which should appear now, and yes, it does. So as I said before, there is this bug which I'm surprised it didn't pick up when I processed the circuit schematic, but it says that this branch with ammeter load doesn't have a resistor. And I was expecting this, and let me show you what that is. So you see here, there is this ammeter load, which is where we had the variable resistance and the variable inductance. Since we had removed the variable resistance and the variable inductance, and we had later connected this current load, there is a 0 resistance branch from this node until our load circuit. So for example, from this node to the node which I just mentioned, there is a 0 resistance branch, and that is a bug. So for example, what I'm going to do, I'm going to just delete this, bring it down, and here I'm going to put in a resistor. Let me call this feeder. What do I call this? I'll just call this feeder 1. Right? So this is a parasitic resistance that I'm going to put. I'll have to go back. Since I made a topological change, I must go back and run my circuit again. So let me go to add circuit file, process circuit schematics, and there are no errors. But remember, because there is this new element which will have a default value, we must go and change it. So for example, this resistor feeder 1 has a 100 ohm resistance, which is way too large. Our objective is just to have a parasitic resistance. So I'm going to make this 0.01, which is like just a feeder, a wire resistance. And let me run this. So it says the program is running, but always go to the command line, make sure there is no error. So you see now that there is no error, the program is indeed running. So if I go back here, I can add a plot, and let me just say current plot. And let me add, you can add ammeter V in. Just say current I, save the waveform, click on done, and click on plot. And you see there is a current plot. And this current plot is actually quite obvious. You see that we have a single phase voltage source with the RMS voltage of 240 volts. That corresponds to a peak of around 340. Since we have a 100 ohm resistance and no control voltage, we are getting basically voltage divided by the resistance, which is basically divided by 100. And that's why we're getting 3 point something. So this is a pretty basic result, right? But it's now a working simulation. Now the next thing which we got to do, and this is what I'm going to wait for the next class, is how are we going to, let me stop the simulation. Let me go over here and go to the control file. We are now going to add a control to this control voltage source and adjust this variable resistor so as to draw a particular current, right? This is going to be our next agenda. What is important? Now we have a working simulation where we have replaced our variable resistance and variable inductance by a controlled current source, which again is represented by a controlled voltage source in series with a variable resistance. So how are we going to use this to model any variable load, and moreover going further an electrical machine? That's going to come in the next few lectures. So as before, if you have any doubt about what I talked about, please do either comment on this video, on this post, or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week where we will continue with the simulation. Thank you so much and see you soon. Goodbye for now.